Guys, so in our previous lesson we were able to finish flow through what parallel plates, fully developed flow as a matter of fact. So today our second lesson, or our second item we are going to look at, under laminar flow, we are going to consider what fully developed flow through a circular tube. Okay, so we consider the fully developed flow in a of a fluid in a long tube of length L and radius R. We specify fully developed flow so that the ends effects are negligible. So now this is the diagram we are going to use. Okay, so now let's have a representation of the diagram here. Let me try to change it. Will green be okay? Let's paint the green. So let's assume this is our pipe. Okay, so that's what we are having. Big guy here, and we have some small guy here fixed in it. Okay, this small guy here is in the big pipe. So let's try to put it here, right? Okay, so now we can realize that there's some kind of insulation in it. Okay, let's put that insulation. Okay, kind of show. So the fluid is actually flowing through this guy, this pipe here. Okay, now if we draw our axis, the axis of flow and the momentum, the velocity and the momentum, we get to realize that we have our R here, okay, and we have our Z doing that. So from here we get to realize that our momentum, okay, travels in the R direction and our velocity in the what, the Z direction. Get it? Good. So this small tube that we are having within is having a thickness of change in R. Okay, that's the thickness, and the whole length of the tube given as what, L. Okay, good. So if that is the case, if that's the case, then essentially we know that here more R, just like for the parallel plate, R here at the entrance here is 0, and R here at the exit here is what, L. So here we are not going to use L because it's not parallel plate, but it's a tube with radius R. So we have R here. Good. So if that is the case, now momentum flows in, okay, then exit here. Good. Pressure as well inside. Then you know that pressure goes in the opposite direction. So we have it here. Now let's derive the equations that are involved. Now we realize from our previous lesson that for a steady flow, okay, the momentum in, minus sum of momentum out, okay, plus the forces, sum of the forces that we have within our system is equal to what, 0. Good. Now because we are dealing with a tube, okay, a tube. Now you know that someone might say that, okay, so if that's the case, the area of the tube is just going to be pi r squared. Okay, but we are talking about the surface area, okay, because this tube is a hollow, cylinder, is a cylinder. Okay, the tube, the shape of a tube is the form of a cylinder, so it's actually a hollow cylinder with both ends open. Okay, so if it's a hollow cylinder with both ends open, you can complete this. That can, so if it's a hollow cylinder with two ends open, then the area is going to be what, 2 pi r of what, h. You get, of h. Okay, and our h here is the length, which is the L, because remember h is in meters, okay, and L is also measured in meters. So 2 pi l h. Good. Now if 2 pi r l rather, okay, so if that is the case, then let's derive the equations for momentum flow across the surface R, okay, due to viscosity. So now look at, we know that momentum, okay, the force actually, so mass times what, velocity. All right, good. And we also know that the shear stress is what, force over what? Area. All right, good. So if that is the case, then from here we can say that force is equal to what? Stress times what? Area. All right, so if that is the case, and so we can name this as, say, equation 1, equation 1, and say here is equation 2. Now remember that, see that equation 1 and equation 2 both have F. Okay, so from here we can say that mv is equal to what? Shear stress times what? E. Okay, very sensible, very reasonable. So if that is the case, then you say that momentum is equal to what? Also the shear stress times area. So if we come here, let me try to clean this. So if we come to this part here, we get to realize that if if momentum is also equal to stress times area, then the area, which is given by 2 pi what change in RL, will be multiplied by the shear stress, which is what R what Z, okay, which is our shear what stress. All right, good. So if that is the case, then this one here, the area, which is 2 pi change in RL times the shear stress across this surface R, across the surface R. Now we look at the momentum flow as across the surface R plus H. Okay, and we're also going to have the same thing here. We are basing on the same analogy that the shear stress times area is also equals to momentum. Good. Oh, shear is not X, it is Z. Okay. We are not dealing with we are not dealing with a rectangular. Good. Z. Good. So if that is the case, then we have been able to derive our equation for both momentum in, momentum out. Good. Now the forces that are involved. Now if we are able, if we tilt this our diagram, okay, let me try to erase here so that you see what I'm talking about here. Okay. So if we tilt our diagram here, if we tilt our diagram for it to become vertical, see this one is lying horizontally, so if it becomes vertical, okay, then it means that gravity is also what? At play. Okay, gravity comes into play. You get that? So if gravity comes into play, then we have to calculate the force exerted by what? Gravity. Okay, the force that is exerted by gravity. Now we know that, so let's try to calculate that force. We know that force, okay, is equal to what? Mass times what? Gravity. Good. And we know that density is equal to what? Mass over what? Volume. All right, good. And volume is equal to what? Let's say area times maybe height or length. Okay, good. Now look at this. We know the area of the pipe. We know the area of the pipe, which is what? 2 pi changing RL, right? And we know the H. Here we know the thickness. The thickness is what? Changing what? R, right? So it means that the volume of this is going to be what? 2 the area times what? The change in volume. All right, good. And we know that density is what? Mass over volume. So if that is the case, the mass will be equal to what? Density times what? Volume. All right, so if that is the case, then you have to multiply. We know the volume here to be this, then you add the density, so times density. All right, good. So if that is the case, we have been able to calculate our mass, leaving our gravity. So the whole expression here is for our calculation of mass. Then we just multiply by our gravity G. Okay, so that is what we are having here. Then I get to 2 pi change in L, change in R what? L times what? Our gravity, right? I think I missed one. We have R, so you bring it there. Very important. Very good. So we have been able to calculate for what? The gravity force. Good. Now let's look at the pressure exerted on the surface at what? R Z equal to 0 and Z is equal to L. Yeah, equals to length. Okay. So here we are just going to have, you know that pressure is what? Force on what? Area, right? Good. So if that's the case, then force will be equal to what? Pressure times what? Area. And we know our area, okay, to be 2 pi in RL. So our pressure for in, pressure naught, so we have the pressure naught, so PO then times our area. Now it comes to the out, because it is in the opposite direction, introduce our minus sign, then we have the PL, that is the exit pressure, okay, to area times of pressure. Good. So these are the equations that are involved, okay, when it comes to momentum flow through parallel through a circular what? Tube, right? So we are going to actually base on this equations that we have been able to derive, okay, to derive our differential equations, and as well as the corresponding equation, the shear distribution, the velocity distribution, right, the average velocity, the maximum velocity, and the volumetric flow rate. So guys, see you in the next lesson as we derive all these equations.